And thank you very much for being here now for the last talk actually of this event. This has actually been pretty amazing 2 days. It's really nice to see so many female researchers and data scientists. So I was asked to say a little bit about myself. So I'll just tell you maybe where I come from. So I started out studying pure mathematics and philosophy. So I started out really from a very theoretical background, and then slowly moved, became interested in computer science as well. Then moved through theoretical computer science actually to an area that's called learning theory, and that is very closely related to machine learning actually. And what I would like to do now is tell you a little bit about this general area of learning theory, tell you about how this has influenced the development of many of what we know as successful machine learning tools, and then also want to share a little bit of my own work with you here today. So. I don't think I need to convince anybody here that machine learning is these days a technique that is really used in many application areas. We've heard about many of the applications that I put here. Actually, we've heard in the last 2 days. So maybe let me just jump right into what is the problem actually that we're facing in a machine learning prediction problem. So let's think about a classification problem. So it could be, an image classification problem, right? So we're given images, and we want to figure out something about the images. For example, is there a face in this image, right? So what is the task? So we're given data, right? What we typically do is we fit some sort of a function to this data. And what are we really after? Well, we're really after being able to predict what is the label of a data point that we haven't seen yet. So the question that we're really facing is how well will this predictor that we learned based on this data, how well is it going to perform on unseen data, right? And from a mathematical perspective, I would call this, what is the true error of this function? So what we typically we observe how well a function is performing on the data that we see, but of course what we don't observe is how well is it going to perform on all kind of data that we may want to apply this to. So this is a very basic question, and here is essentially the only formula that I'll use in this talk, although it's a talk on theory. So what we know is that what I would call the true error, what is the error of this function with respect to the underlying unknown data generating process, we know it's bounded as this, right? So this is pretty obvious inequality, right? So it's bounded by, so how does this thing actually? Okay, so this true error is bounded by the error on the data, what we call the empirical error, plus obviously how large is the difference between the true error and the empirical error, right? So the quantity that we really want to be able to bound somehow is this difference between the empirical loss or the empirical error that we observe on the data and the true error. And we want this to be somehow bounded by some function. Ideally, we believe that this will go down as we see more and more data, right? So if we have our favorite tool that we use for machine learning, we would expect that the mistakes that we're going to make on new data will go down as we see more and more data for training, right? So we're really interested in this quantity and how it depends on how much data we see, right? So now what I would like to do is I'll take you through a very brief and quick tour of learning theory. How has learning theory actually addressed these problems? So let's go, I guess, 50 years back. So in the 70s, there were 2 Russian mathematicians, statisticians actually, Vladimir Vatnik and Alexei Shcherboninkis, and they came up with a characteristic of a class of predictors that will allow us to bound this quantity that we're interested in bounding. So they, and if you have heard anything about learning theory, then you may have heard about this quantity, which is the VC dimension of the class. So this is a property just of the type of predictors that you use. For example, of linear predictors, it's related to the number of parameters that you need in order to specify a function, right? So for linear predictors, it would be essentially the dimension of your space, bounded size, say, neural networks, you can bound it, bounded size decision trees, you could bound this function. And what it tells you is that, if my function class is bounded VC dimension, then as I see more and more data, I know that the true loss of every function in this class is going to be very close to the empirical loss that I can actually observe, right? So this really gives us, from a statistical point of view, very nice control over this difference of the empirical loss and the true loss, right? Okay, so now let's jump one decade. So what happened in the 80s? So in the 80s, so this is now in North America, Les Valiant came up with a theoretical notion of what it means to be learnable. So this is a mathematical notion, so you don't need to read this, this definition. The only thing I would like to point out here is, so what was added to these considerations of Wapnick and Chervonenkis before, and Wapnick and Chervonenkis were really interested in a statistical problem, like how well does the empirical loss that I observe represent the true loss, right? So now here what was added in this, say definition of what it means to be learnable is this requirement that there actually should also be a method that implements this, right? So there should be a method, there should be an algorithm that takes in data and then somehow, computer scientists would say, polynomial time, that's good enough. Of course, we may have stronger requirements on what it means to be efficient, but this aspect of efficiency, computational efficiency, was added into the picture. Beforehand, it was really pretty much a statistical exercise, and now what this was saying is, no, we actually also need to have efficient algorithms that will allow us to do this, right? And then, so then, of course, the next question is, when is this, now that we have a definition of learnability, when is this actually fulfilled? When can we fulfill it? And from a statistical point of view, this was, actually already, pretty well understood. We know that, we have this successful learnability if and only if a class has bounded VC dimension, and there were also other characteristics that could lead this. For example, bounded compression sizes. So very much what was understood at that point is already that, if we want to have good control of how our errors, how our losses develop with the data sizes, we somehow need to use predictors from a class that had somehow bounded capacity. So we need to prevent what is known as this phenomenon of overfitting that I'm sure you've all heard about. We need to somehow make sure that our function class is not so flexible that it's just going to adapt to all kind of noise in the data and then not be representative of the underlying process at all. So that was well understood in the 80s. But what was also realized then is that for most function classes that we actually would like to use, this is actually a computationally hard problem, right? So, so then people were really starting to work on this relation or the connection between the statistical efficiency and the computational efficiency. So really the problem became, well, how can we, on the one hand side, guarantee the statistical requirement that we want to have a good performance on unseen data, while at the same time have efficient algorithms that implement this. And that, in the 90s, led to, maybe two of the most known and successful learning tools. So Freund and Shapiro developed what is known as boosting. It's still widely used. We've heard about it in the talks before. Method. So really here the story was that once we know that most of these classes are actually not efficiently learnable, well, they were asking, well, maybe can we at least do somehow better than random guessing while being efficient? And then what Rob Shapiro showed is that actually we cannot. If we also have a requirement on computational efficiency, then just learning, to be slightly better, like be by some fixed small gap better than random guessing, is as difficult as learning to arbitrarily small error, right? So that was kind of a theoretical. It was a lower bound. It was reduction, that showed, well, no, actually weak learning we cannot do. But what happened then is then people said, well, let's just pretend that we can do weak learning, and let's turn this reduction into actually a practical tool. Let's pretend that we have weak learners, and this is, then we have this reweighting method that will actually lead to having a computationally efficient method that also leads to arbitrarily small error. So what happened is that this, negative result was kind of turned on its head and turned into a successful practical tool. And then, around the same time, support vector machines were developed. And again, this is, came from this, consideration of computation and seeing that, requiring for a predictor to have a large margin is actually equivalent to minimize what we know as the hinge loss function, which is a convex loss function rather than trying to predict, trying to actually minimize the prediction error in a classification problem. So what was developed here is kind of the connection between large margins and convex loss functions, and that then leads to what we know as support vector machines. And then, of course, also the theory of kernels turned this into a generally successful tool that goes beyond learning just linear classifiers. So both boosting and support vector machines really started being practical methods in the 90s. And then, in the next decade, things started to be going well for both for machine learning from a practical perspective and from a theoretical perspective. So there really were in this time various concepts that lead to good generalization performance that were discovered. So for example, VC dimension is just one concept that works for binary classification, so it's relatively restricted. So people came up with Rademacher complexity, data-dependent generalization bounds, Pak-based bounds. Also, people were starting to look at, how do properties of a learning algorithm, rather than of the type of predictor that we use, how can these lead to good generalization performance? So things were, understood better and better. And basically, we're still in this mindset that the error that we should be expecting on test data, on data that we have not used during training, should have somehow be dependent on how well is our class going to fit our training data, plus some sort of capacity of the class, right? So that was still the general belief. And then what happened in the next decade? So then, I guess as we all know, since 2010 to 2011, all these the method have really been taken over by deep learning. So we've heard examples of this, right? That deep networks have been very successful at image classification tasks. Also have been now very successful in reinforcement learning, playing games. The issue from a theoretician's point of view is that these classes have huge capacity, and really this shouldn't work, right? So so this is from a theoretician, we were really in beforehand being in the situation where it seemed like machine learning theory and practice are working very closely together. But now it seems like, well, these things work, and nobody really understands why. But there was still some belief that maybe we just don't understand them well enough yet. Maybe we just need to think harder. Maybe we just need to figure out what it is in these networks, or what it is in the training methods that we use that actually make these predictors generalize. And then came this paper. I don't know if how widely this is known, but this was really kind of shaking the theory community. It's a paper by Zhang, Bengio, Hartrecht, and Vinyals. called Understanding Deep Learning Requires Rethinking Generalization. So what they did is they did 2 experiments. They trained deep networks on some image data. And what happened is, training error goes to 0. So these, really are high capacity classes that can fit to your data really well. And they also generalize. So this is what, should have been expected. And then what they did is they randomly permuted the labels. And what happened, the network was still able to fit the data, but it doesn't generalize at all. Right? And the disturbing, from a theoretician's point of view, disturbing aspect here is that it is the same type of class and it is the same learning algorithm used. Still, in the one situation, we have generalization. In the other situation, we don't have generalization at all. Right? So this is kind of depressing from a theoretician's point of view. So now I'll switch gears a little bit. I'll come back to this example towards the end of my talk. So what I would like, at this point, it really seems like maybe we're in a lost situation. Maybe theoretically we won't understand why these methods actually work. Maybe we should, give ourselves a break with trying to tackle this this problem of generalization and just see, maybe what other considerations do actually come up these days. Since machine learning is used in so many different areas right now, there's all kind of new problems that we should maybe be looking at and try to understand better. So in terms of efficiency, it's not just this question of how much data will lead to how good prediction error, but also we can ask ourselves, can we maybe get away with less labels? Can we maybe have the algorithm be interactive and learn better through that? We've heard about these issues. We've heard several times that really there's a need for explanations to come with predictions, to have interpretable classifiers. We yesterday heard a very nice talk about this issue of causality. How does that affect or interact with learning? And of course, there's also all kind of issues with safety and adaptation that I think we've also have been mentioned several times in the talks here. So rather than just focusing on this one question of how well do predictors generalize, we could try to understand all these other aspects better as well. And I haven't worked on all these areas, but I have worked mostly on designing interactive machine learning methods and on designing methods that adapt to data shift. So I want to now give you one example of one of my works. Consider this issue that in many situations you train your data, you train your classifier or your regressor on some data set, and then when you want to employ it, maybe something has changed in the data generating process, right? So you have this, you label data, and then maybe there was some sort of shift that happened. And the question is, can the predictor that we learn, can it still perform well on this new type of data, right? And can we do this in a way without having to fully retrain the predictor that we use, right? So this is kind of a often faced issue. So often in these situations, maybe we have training data, label training data that we learn some predictor on, and then on the new task, we have lots of unlabeled data, but we didn't have anybody to annotate all this data yet. Right? So now the question becomes, can we somehow get away, can we manage to learn a well-performing predictor on this new task without having to actually relabel and relearn the whole problem? Right? So here's a very simple rule that you could use. So the rule that we set up, it's a nearest neighbor rule. So say you have 2 parameters, we call them k and k prime. You can think of, say some number that you want to use maybe for k nearest neighbor prediction, and then twice this number or 3 times this number. So what you do is you go over your new data, your unlabeled data, and you look at a k nearest neighbor ball. So you look at the ball in your data set that contains the k nearest points. You ask yourself, how many labels do I have in here? If I already have sufficiently many labels, I'm fine. I say, well, this area is well covered. I don't need to do anything here. But if you're in a situation where most of your nearest neighbor points are actually, say, not labeled, so they come from the new task, you would say, okay, maybe here I need to get some extra label supervision, right? So this is, the method in a nutshell. We just say, you go over your labeled and your unlabeled data, you do this querying rule, and then you use your now labeled data set to, say you just use a k-nearest neighbor predictor on this new data set. Right, so what we showed, so here's, one, I'll show you one theorem, one, instance of what the result in learning theory would actually look like. So what we showed here, so again, you don't need to read through this text, but essentially what we showed is we showed a bound on the expected error of the classifier that you'll end up with if you use this label querying rule. And the main thing to observe here is that essentially this bound looks like essentially the same bound that you would get in a no data shift nearest neighbor for nearest neighbor prediction without any data shift, right? So what this rule or what this rule for interaction did is that on the one hand side gives us the same type of error guarantee, the same kind of behavior that we would have had there been no data shift. But of course, this you could get by just saying, well, label all my new data and just use that, right? So that is not so surprising in itself. But at the same time, this method will make sure that if there was no data shift or if the data shift was not so significant, then it will actually not query. So it will not waste resources. Right, so this is kind of the two main characteristics that we can, on the one hand side, we can guarantee correctness without having to make, strong assumptions on what type of data shift happened. And on the other hand, the method will automatically adapt the resources it uses to the difficulty of the task, right? And I guess I have to speed up a little bit. So this is, so this is just repeating this principle, right? So what we want to do is we want to still design methods in a way that are agnostic of the actually underlying environment. So this is what all these earlier work in learning theory really stressed on, is that we want to have bounds that don't depend on assumptions necessarily on how the data was generated, but only on factors that we actually have control over. But at the same time, we want to maybe design methods so that they will request resources according to the difficulty of the task, so that we can actually guarantee correctness. Okay, so how was this? So this is a very simple example of such a rule. And what it's based on is actually, understanding the, asymptotic behavior of how nearest neighbor balls or how nearest neighbor prediction actually works. And this is, what I left out in my little history tour of machine learning theory. So this was a little tour. So what I left out, that even earlier than that, even earlier in the 70s, people were already thinking about these type of rules, nearest neighbor prediction rules, and analyzing them in terms of properties of the data, right? So we already had generalization bounds for these type of predictors in the 60s. Okay, so now I'm just going to speed up. Right, so what is happening here is really that the type of analysis that we may want to do, and that becomes very often necessary when you don't care just about generalization, but about all kind of other aspects like interaction, like use of unlabeled data, is that you get these improvements from these other resources as a function of how easy or how difficult your learning problem actually was. So and then just two side comments is, so this very similar rules have very recently also been used in order to define, so you can say, well, this was just for nearest neighbor prediction, right? Is that actually how is that relevant? But very similar rules have been used to get confidence score also for lots of other type of predictors. And if we now look back at this problem of neural networks having huge capacity, being able to fit random noise, so maybe a similar thing was actually going on here, right? So maybe the performance that we get on deep networks is not so much an issue of what we were concerned with before, with like capacity of the class or properties of the learning algorithm, but maybe what really comes into the picture here is the difficulty or the smoothness of the underlying data problem. Okay, so now this is just my final comment. So there's lots of, so instead of being all focused on just this question of generalization, there's lots of other aspects of machine learning that need to be better understood and addressed these days. And there's many aspects actually that really require theoretical understanding issues such as fairness or privacy. Typically, they involve trade-offs between the predictive performance of the say the classifier, the regressor that you output, and these other requirements. So yeah, so I would like to invite you to look into the details of the methods, or let's look into the details of the methods that you're using and really try to understand what type of inherent biases they have and what kind of trade-offs they imply. Thank you.
So any questions?
So what do you see in the future of deep learning and understanding deep learning? And I know you said that it's necessary to have a formal understanding, but do you have a sense of what that means more specifically?
Yeah, I mean, this is, what I was trying to, what my suspicion is right now is that we'll probably maybe see a similar type of analysis, type of understanding to what we've seen very early on actually for nearest neighbor. So nearest neighbor prediction is similar in the sense it also has huge capacity, right? It can also just fit any data set, but it has this universal consistency property as well, right? So nearest neighbors, if you adapt your, the number of nearest neighbor that you use for your prediction, it's shown to be a universally consistent method. The problem with nearest neighbor prediction is, of course, that you need to store your whole data set, and it's computationally horribly inefficient, right? So we can't use that, right? So maybe these are really methods that allow us now to have computationally efficient, high capacity prediction that will maybe exhibit similar properties. So that's my suspicion. But, I think right now my impression is that many people are looking at this problem, and everybody looks at it, of course, from their own angle, and tries to find the explanation from tools that they've worked with before. So you see lots of different attacks, but I think it will involve stepping away from this aim at uniformly treating hypothesis classes, trying to say, oh, here's my class, I understand my class, and now I get a guarantee for all functions in this class. This is probably not going to happen. It will probably involve also understanding what is a natural learning task.
Well, I hope you are able to get this understanding. Oh, sorry, was somebody else speaking? No? Okay. No, I just wanted to say, thinking about what neural networks do is really hard. So I hope that we can reason about them better with these things. Yeah,
that's a general.
Hi, thanks a lot for your talk. I was wondering, so if you create a data set and you have images where, the nearest neighbor approach maybe is not one that is completely feasible. For instance, if you have, well, if like your region of interest is quite small, or if something that you can't really predict very easily, and there's a lot going on in your image, so basically it's not just like you have faces or dogs or something like that that you need to classify. Could you imagine that there would be an extension to the approach that you could generate a new data set with maybe a more sophisticated approach other than the nearest neighbors?
Right. So I mean, this type of nearest neighbor is based on having some sort of distance function on your data, right? And typically, if you have images, you don't use just I don't know, Euclidean distance between your pixel representation of the images. Right. So typically, what you would have is a different representation of this data, which could give you access to different distance measures or kernels. And I think this is something that has been used for image data. So you don't want to use this like raw idea as is on images, but you could use different. It's a matter of finding a good representation where these distances correlate well with the labels.
Do you have any examples maybe of techniques that would come to mind for
so I'm not an expert on image classification. So, but this is used for images, right? So
yeah, because I've seen a lot of people using nearest neighbors in order to classify images, and this is in a pixel space, so it's exactly that.
Yeah, so you want to use a different kernel, different distance function.
Thank you.
And thank you very much for the wonderful talk.